So you've screwed up and dropped your pet Milsurp hunting rifle on the rear sight and completely bent the rear sight. And that kind of sucks. So you're going to have your local gunsmith sort this thing out, and you ask yourself the question, why does it look like what it looks like? And how do I check that when he unbent it, it still hits to where it says it's going to hit, to all these funny little metric numbers? Let's jump down a rabbit hole and take a look. All right, this is my water cannon. We're outside in the parking lot. There's cars driving by, whichever. I made this rig to prove a point. The sights don't move. We're looking through the rear sights at that clamp in the front, and it's looking right at the bucket. And as we turn this thing on, we're at point blank range. The water hasn't begun to drop yet, and we're going straight onto the bucket. Okay, but let's say we want to go a little further out. Let me move the bucket a little further out here. Uh-oh. The water's not hitting the bucket anymore. It's dropping through. Why? Because the gravity is pulling down on the water, and we can see through the sights, and I think we can see the whole thing here. The water's just not quite getting there. You can plainly see here, we started about with the top of the washer at our datum line, and this is where the projectile, the water in this case, is coming straight out of the cannon, and it's just dropping down and hitting the ground harmlessly in front of the gun. So what I'm going to do is I'm going to make a sight correction here, and the important point to note is that we don't move the sights, we move the gun. So as this keeps moving backwards, we can keep, there we go, that's lining up. The camera that's pointing through the sights, we're never moving the sights, we're moving the gun. But the thing to note here is that to increase elevation, the distance from the breech of the gun, here we go, we gotta keep going. That was a big move right there. I went from 3 units to 10 units, and we're in the bucket now. We're not moving the sights, we're moving the gun. So in order to increase elevation to make the water go further, the distance from the breech to the rear sight got larger. So when you're moving sights, the point I want to make is you're moving the gun, not the sights. That's the important part about all this. We were going to build a ballistics chart for water. We were going to do a couple of things here. This whole rig isn't really predictable enough to be able to do that, but hell, it's fun to play in the water. Water has trajectory. It has mass, therefore it is affected by the gravity of the earth. Everything drops. There is a distinct curvature to this. The wind's blowing it around. All of this happens to your projectiles. So if this makes it any easier for y'all to take a look at, let's just stop this and we'll chop one, and that's essentially what we're doing, is we're just shooting a projectile out. In this particular case, a dihydrogen monoxide cannon, but you get where I'm aiming at. Let's go inside and have some theory explained to us by Reed. Do some of that engineering stuff, Reed.
So before we can talk about trajectory, first we have to have our bullets impact where we want them at a known distance. So let's say we're taking this thing out to the range at 100 yards and it's shooting like 12 inches low. So we know we need to raise this rear sight up here, but I mean, how much? Is that too much? Is that not enough? Like, it's hard to know. So how much exactly do we need to raise the rear sight up by? That's determined by a couple of factors. One of them is the length of the sight radius. So from the tip of the front sight to the back of the rear sight, it's just about 31 inches on this gun. So we have the distance from the front to the rear. We have our distance we are away from the target, and we have how low it's impacting. So we can find now how much we need to raise this rear sight up by. So what we have going on are two triangles. The first triangle is the distance from the front sight to the rear sight, this distance here. And then the other one is us and the target. So you know the distance from the front to the rear was 31 inches. And the distance from us to the target is 100 yards, or if you convert it, 3,600 inches. That's that length, that's that length. We know it's shooting 12 inches low. What we're trying to find is this right here. How high we're going to raise our rear sight. So these two triangles are the same in their ratios. So we'll have a constant C. 31 times C equals 3,600. And if you divide both sides by 31, C ends up being 116.12. So now H times C is 12, and we know C. So that our height that we need to do times 116 is 12. We're going to divide both sides by that. The height that we need to move the rear sight is 103 thousandths of an inch. A 103 thousandths of an inch is that right there. So it's not a lot, but it's also not an insignificant amount. So we need to raise this rear sight up 103 thousandths of an inch. Without a pair of these, that would be very difficult. But we'll find our 0 point. 0. We'll go an additional 103. We'll bring it up until it touches. There it is right there. So this concept doesn't just apply to elevation. It also works the exact same way in windage. For the rear sight, if you want the bullets to impact more to the right, you move this sight more to the right. If you want it to move more to the left, you move it more to the left. Now, some guns have an adjustable front sight, and that then is the opposite of the rear. If you want the bullets to impact higher, you actually take more off, then that would be your sight radius, and then the bullets would impact higher. So it's all relative. But your front sight is going to be opposite. Your rear sight is going to be in the direction you want the bullets to impact. Ready? All right, let's demonstrate how this all works and go to the range.
So the sights are level and they're pointed directly at our target. And as we're going to demonstrate here, the gun's going to move, not the sights. That's the other thing I want you to see. We're going to pull this away now, take the range hot. The level's away now. We're going to charge the gun. Range is hot. You come off safe. There's no one downrange. Spotter's up. Send 2 at the 400 meters setting. Outstanding. Sight move, 800 meters. Range is clear. When ready, spotter's up, 2 rounds, 800 meter setting. Outstanding. Set for 200 meters. Two rounds. Range is clear. Spotters up. Send them. Outstanding. Set for 1/600 meters. Range is ready. Set it. 1/600 meter setting. Outstanding. Set for 2,000 meters. This is maximum sight elevation at 2,000 meters. When verified, 2 rounds. Range is clear. Spotters up. Flying in with the bubble, we can see that the gun's now pointed up in the air and the sights haven't moved. Let's go down and take a look at the target. Reed was aiming at the Anvil logo. 400 meters, 2 holes right next to each other. 800 meters, 2 holes. 1,200 meters, 1/600, and the 2,000 meter holes aren't even there. They went clear over this piece of paper at 50 meters. So you can see there's an incremental progression, and that's what we wanted to show. Where these are going to hit, however, that's a matter of conjecture. It's a hot day, and I don't know if it was this hot when that sight was calibrated, and therein lies the rub. So the sum total of all this talking and everything is the fact that this is an analog computer, and the ballistics of the round are memorized in this analog computer on one day, at one temperature, at one altitude. This is right, probably once. So are these sights correct, even if it was 100 years ago and we happen to have the right ammunition? Probably not in Charleston. But we can't have the ammunition from back in the day because we don't have it. So if you look at the two computers, look at the programming. This is a black powder round. This is 10.4 by 38 rimmed, 41 Swiss. Look at the ballistics on this thing, man. I mean, it was like toss bombing. Look at that. This particular ballistics curve, let me pop these both up out of the way and take a look at it. This is a representation of a black powder round. This is a representation of a high velocity 8mm Mauser round. That's all this is an analog computer that's remembering things that it was told, and it's only right once, and you cannot change the programming of the computer. You know, and that brings me to one other thing that I've been meaning to bring up. And that'll keep any smarty pants from getting after me. Well, this is a demo that I've had to do before to show some people something about the limitations of the human eye. So I'm going to paint this, and most of my left hand, fluorescent orange. And I'm going to take a little stroll on a 95-degree South Carolina day. We're going to paint that fluorescent orange. Rick, incoming. Got it. Paint that fluorescent orange. And I'm going to go take a little stroll in 1 meter steps. 1, 2, 3, 4, 5, 6, 8, 9, 10. 50. 100. 150. 200 meters.
Okay, ready. B-roll 44 Magnum.
.44 Magnum, America, Yeah.